In this lesson, we will start our discussion on associative containers, and the first associative container that we will discuss is set. And if you understand set, then you understand the fundamental of other associative containers. So instead of accessing by some index, here we have a key value association. And in the case of set, there is no value, key itself is the value. So in terms of mathematics, set, a normal set is a group of elements which does not allow duplicates. Similarly, in C++ also, this set will not allow duplicates. We have another version of this called multiset, which allows duplicate keys. So let's study about this normal set. It contains a sorted set of unique objects. So here this set contains it in sorted order, and it uses the compare function that you can see here to order the elements or sort the elements. We also have an unordered version called unordered set, which does not contain the order. That's purely a hash table. And here, in order to work with this, you need to include set. And then you can also provide your own compare. If you don't provide, it will be std less. So it will sort in the ascending order. Let's say you have a set of integers, then the smallest integer will come first. But let's say you are creating a set of some custom defined class, then this less than the standard less will not work. So you will need to define your own function, own compare function for that. And we will see an example of that also. An allocator is there, which is the default std allocator. You can, if you want to know more, you can study about it, and you can create one int pointer and then std allocator dot allocate 2, 3 in order to allocate a space for 2 integers, 3 integers, and so on. You can explore more, although you don't need for using set. Then what is the time complexity of different operations? So it enables you to insert elements into the set and also remove elements and also find elements. So all of those will be of the order of log number of elements, and this is maintained with the use of some balanced binary search trees, and usually it's red black trees. So the red black tree is balanced by the red and black properties. So we have a tree where the root will be black and its children can be red or black, but a red cannot have red child, so double red is not possible. So this is invalid, but you can have double black. And another property is that all the leaves will have same black depth. So let's say this is the red black tree. So you see that these are leaves. So its black depth is number of black nodes from this to root. So it has 1, 2, 3. This also will have 1, 2, 3. This also will have 1, 2, 3. Although in total they can be at different depths, but black depths would be same for all the leaves. So using these two properties, that no two red can occur and black depth of all leaves is same, it maintains the balanced search property. How? Because the smallest depth, let's say this is leaf, and of course this will be black. So this is root node, and the closest leaf can be here. Let's say the black depth of all the leaf nodes is 4, and largest can be when we have alternate. So this also has a black depth of 4, this also has 4. So this can be closest at 4, and it can be maximum at 7, its depth, overall depth. So it cannot be 2 or more times the closest node. So this is kind of balanced, and you are able to maintain all the operations in log of n, because height of this binary search tree, balanced binary search tree, will be log of n. Now let's see some of the functions that we can use. One is size. It will give you how many elements are there in the set, and it does not allow duplicates. So if you insert same number multiple times, only one of them will be inserted. Then equal, you can create one initializer list and assign to it this set. And we will see example of all of those. Clear, as the name says, it will clear all the elements, remove all the elements from the set. Count, here you need to pass the key and it will search the number of occurrences of that. In this case, it will be either 0 or 1, depending on whether it's present or not. Find will search for a number and return the iterator to that number. If it does not find the number, it will return set.end. That is, it will not point to a valid index but beyond the last one. Empty is used to check whether there are any elements or not. Then we have insert and erase, which we will see in some detail because they have multiple versions and all of them can be useful. So we will discuss about them in some detail. And you can see a few versions here. In one case you insert a key, and then in other case you are passing two iterators, then you are passing an initializer list. Return type will also be different depending on which version you are calling. Similarly for erase. Then we have upper bound and lower bound. So in upper bound you try to find all the, it returns the iterator. So here there is a sense of ordering. So let's say you have 5, 10, 12, 15, 20. So in this case, it will return, let's say we are calling upper bound 10. So it will return greater than this 10. So it will start from 12 and you can iterate till the end. So this upper bound 10 will return 12 and lower bound 10 will return 10. So greater than equal to. So this is the difference. It can be useful in some scenarios, though not very frequently used. Now let's see the insert and erase different versions in some detail. So if you are inserting a key, like you have a set S, let's say set of integers, and you are inserting s.insert 5. So this will insert 5 here, and this version will return a pair consisting of iterator to inserted element, in this case this, or element if it's already present, then it will return that only, because let's say you insert 5 again. So it will not insert again but return you this iterator. And bool value, which will denote whether insertion took place or not. So it will return a pair. Next is you pass two iterator positions. So here clearly you will not want to insert elements which are already there, they will not be inserted. So these iterator positions will be like some, let's say you have a vector of int and it has a few elements, and you want to insert from this to this position of this vector into a set. So s.insert, let's say you want to insert everything, then v.begin, v.end, and it will insert all the elements. If they are duplicates, it will insert one of them, not all. And it can be used in some scenarios where you have a vector and you want to create a set out of that. So you can do it in one line. And it does not return anything. Similarly, if you insert and then s.insert and you pass a initializer list like 10, 12, 30, 40, then it will insert these elements into the set. And again, if there are duplicates, which one will be inserted is not defined. Similarly here, if the vector has duplicates, which one will be inserted is not defined. Then returns nothing as this one. So these two versions are not returning anything. Then let's come to erase. Here you can either pass the iterator position. In that case, if you actually have a pointer to the actual number, then better pass that iterator position. If you don't know the position, you just pass the value. Like in this case, here you pass the position. So here it returns the iterator following the element that was removed. So let's say it was 10, next was 15. And you called, this is IT. If you don't know IT, you can call set.find10, it will return the iterator. So it will return this 15, the next one. And here it will return the number of elements removed. So if this is not a multi-set, it will be 0 or 1. Then we have erase with 2 positions. Let's say it has more elements. You want to remove from 10 to 20. So you will pass this one and one pass to this. So this one, last one is excluded. So you see this square bracket here and open here. So this is closed interval, open interval. So POS2, the second iterator, is excluded. So if you want to delete 10, 15, 20, pass this as the first iterator and this as second iterator. Now let's see example of these. So first you need to include the set header. So we are putting in random order and even duplicates. Then we will print and see that these are ordered in sorted order and also duplicates are removed. So 10 is there. We have inserted 10 2 times, then 15, 20, 20 is also twice now, 4. Let's print the size. Then we will insert a few elements. 100. So 100 was not there, so it will be inserted. If we insert 10, it will not be inserted. So here size should increase by just 1 after these 2 insertions, because one of them is not inserted. Now let's print all the elements of the set. Val, or rather call it elements of set. And let's see. So size was 5 earlier. And what were those 5 elements? 10, 25, 15 and 4. Then we inserted these 2 elements, but 10 was already there. So only 100 is inserted. And now size becomes 6. So these are the elements that are in the set. And you can see these are sorted because the default comparator is std less. If you make it std greater, it will be opposite. Now let's do some more operations. Let's erase something we have inserted. Now is the time to erase. First we will erase with iterator. So it will return an iterator. And the iterator that you are passing, that you want to erase, must be valid iterator and must be dereferenceable. For example, s.end is also a valid iterator, but it cannot be dereferenced since that's not pointing to any of the elements in this set. So if you pass such kind of iterator which is not dereferenceable, then it will crash. So what iterator we want to delete? Let's say we want to delete this 10. So it will be s.find 10. You can also pass 10 here, but it's for just demo purpose. I am first finding the iterator and then passing it here. So it will return the iterator following 10, that is 15. So if we print this star it, it should be 15. And it's 15 as you can see. Now let's comment these. Now we will delete 10 again, but this time using the value num erased. How many elements are erased? Of course, if it's there, it will be 1, not more than 1. s dot erase 10, cout num erased. So it's num erased 1, and if you can again print it out here, and 10 should be gone. Next we will take a look at the upper bound. So you can see 10 is gone here. So upper bound also returns one iterator, so let's capture it in UB or just UB. Seven, so more than 7, so 10 is already removed, so it should return 15. Or just print UB. I was trying to iterate from that element till the end. So it's 15. Now if we pass 15, then it should return 20. It's 20, but if you, instead of upper bound, you make it lower bound. Let's name it LB. It should be 15. So that is the difference. So greater than equal to and greater. So if you pass 10 here, both will be same. Both will be 15. Because 10 actually does not exist now. So it can be useful in some scenarios. So keep track of that we have some upper bound and lower bound functions. Next, we will start inserting our custom classes, so that we need to define our own custom comparators. So let's say we have a class called student class. So let's define one. And student will have ID, student ID. It will have a name. It will have age. Let's keep just 2 variables for simplicity. And we will compare on the basis of ID. So this should be string. For primitive types, I did not give example of sum of inserting with initializer list. So let's do that also for the sake of completeness. So s dot insert. Let's pass a initializer list. -10, -30, -20, and let's print it again. So you see these are inserted in the order. -30 is the smallest. Next, let's insert by passing 2 iterators. So let's say we have a vector. (10, 20, 15, 5, 4). Some of them are duplicates, so not all of them will be inserted. So we want to insert everything from this vector to this set. And then we will print it. And we also need to include the vector. and these are inserted. Those which are duplicates are not inserted. Next we were coming to this student class. So it has ID and name, and then we need a comparator. So we will define, so let's keep everything public. Although it's not recommended, you should keep these private. So we will have one less than, we need to define that less than operator. So we will have bool operator, and this one so it's a binary operator, two operands. The first one will be this instance, this instance of this student, and we will have one other. And let's make it const and return this ID less than other.id. So this will be for sorting in ascending order. If you want descending, make it opposite. Let's also define a function for printing it. The class, you can also overload this operator, but that will involve some concepts like friend functions. So just make it simple, print student. Now let's create a set of student classes. So you can create objects and then also insert, or you can directly pass the parameters, these ID and name in this order, and it will construct student objects from them. So let's say we have first one's ID is 50 and its name is Simon. Next is ID is 20 and its name is Thomas. Just two students. Then let's print it. We have already print a student, so st, and let's see what order they are printed. So first Thomas is printed because we are comparing on the basis of ID. Let's change it. So here Thomas was printed, that is ID 20 then 50. Now we have changed it, it should be opposite. So it's 50 first, then 20. So this is how you define your own compare functions. So I hope this was useful, and the same concept will be carried forward to other associative containers. So make sure that you are comfortable using all the different functions of set.